16b. Quartics are not really going to be that different. Here, let me, just a second, I want to be able to write this problem before we do it. And then, so let me write it. It's y equals x to the fourth, that makes it a quartic, minus 4x cubed plus 4x minus 1, and they give you two solutions. They give you x minus 1 is one factor, and the other factor is what, x plus 1? Yeah. Looks like it was kind of an interesting problem. It looks like the original problem, they only gave you one solution.
Yeah.
Which is hard to, that would have made the problem really hard to solve. The fact that they give you two solutions is really cool because, oh, shit. Because I know that I can synthetically divide this by my first solution, 1, and then I can synthetically divide that by my second solution, minus 1, and then I'm going to be left with a quadratic, which I can then use the quadratic formula on. So let's do it. Across the top, I'm going to put my coefficients. Notice I need a 0 for the x squared term. See why?
Yeah.
So my first solution based on that is plus 1. Go ahead and do this. Tell me what to write.
So drop the 1, and then multiply 1 by 1, and you get 5. Or it shouldn't be a negative 4.
Yes, thank you. We would have been all screwed up. Hold on. Which means we don't get 5, we get negative 3, okay. And that's negative 3, and that's negative 3, and that is negative 3, and that's positive 1, that's positive 1. I get a 0. That tells me that indeed that was a factor. In other words, had I not gotten a 0, then 1 is not a solution to this quartic. Now, because I used synthetic division, this is a cubic, but I don't really need to know what it is. I'm just going to divide it by the other solution that they told me was a 0. And that's the beauty of synthetic division, is that you can take your first answer and immediately go to your second problem. So I'm going to bring this 1 down, multiply, add, multiply, add, multiply, and I get another 0. So what is my last factor? In other words, I now have x minus 1 times x plus 1 times this quadratic, which is x squared minus 4x plus 1. You see where I get that quadratic?
Yeah.
Okay. Now, to fully factor it, which they want you to do, because I can see from her key, you got to use the quadratic formula on that. So without looking at her key, tell me how I'm going to solve that quadratic.
4 plus or minus the square root of 4 squared minus 4 times 1 and then times 1 divided by 2.
Okay. Which gives us 4 plus or minus the square root of 12 over 2. And that can be simplified because the square root of 12 is 2 square roots of 3 In other words, I'm going to replace that with 2 square roots of 3. Now I can divide top and bottom by 2, giving me 2 plus or minus square root of 3. So my other two factors are x minus one of these answers and x minus the other answer. See how I did that? In other words, once you found your factor, or excuse me, once you found your solutions, your zeros, these are the two zeros, well, now you have the two factors. It's x minus one of these and x minus the other one.
There you go.
Which makes our solution x minus 1 times x plus 1 times x minus 2 minus root 3 times x minus 2 plus root 3. There's my 4 factors.
Okay.
And that should be what she got. So x plus or minus 1, that's my first two factors. And x equal 2 plus or minus root 3, that's my second two zeros. I guess she wasn't going for the factors as much as she was going for the zeros. You understand the difference?
Yeah.
If I have a 0 at 4, my factor is x minus 4. If I have a 0 at 0, my factor is x.
Okay.
So she found the 4 zeros, and they're the same 4 numbers you'd get from my 4 factors. All right. All right. 19. Divide. Let me write the problem out. There's 2 ways to divide. What are they?
Synthetic and
I can do it by long division, or I can do it by synthetic division. Which way do you like the best? First of all, do you know how to do it by long division? If you don't, we should go through that at least once.
Yeah, I do.
Okay? Then let's do it synthetically. What's going to go in the box?
Negative 1/2.
Plus 1/2. In other words, if this is my 0, then the value for x is plus 1/2. Right?
Yeah.
If this was an x minus 1, you'd put 1 in the box, right?
Mm-hmm.
Because what you're doing is finding what the zeros are of this. And this 0 is 1/2. Now, what goes across the top?
4, negative 7, and 8.
Got to put in a 0 for the missing x squared term. Then minus 7 and 8. And you'd have to put in a 0 whether you were doing long division or synthetic division. You have to allow for all degrees of x. Okay, you pretty good at synthetic division?
Yeah.
Such that I don't need to make you do this?
Yeah.
So that's our remainder, 5. What's our answer?
4x squared plus 2x minus 6.
Instead of writing a remainder, I'm going to say plus 5 divided by our divisor. That's our answer. You don't need to necessarily say with a remainder of 5. You take any remainder you have and you divide it by your divisor. Whoops, that's minus 1, not plus 1. I've been making that mistake a lot today. That should be what her key says. 2x squared. Where was my answer? The heck happened to my answer? Just a second. 4x squared. She factored out a 2. Why'd she factor out a 2? How did I get the wrong answer?
She taught us that usually when it's not like a single like x minus or plus something, and how it's like 2x minus 1 now, to always use the way she did it.
Huh.
I don't remember what it's called.
We better do long division. I think that by trying to do synthetic division, I came up with an error. So let's do this by long division and see if it produces anything different. I'm learning something here that I'm not sure I knew. And that is, if you're dividing by a fraction, you got to be careful. Let's see, 2x minus 1 divided into, hold on, what was the original function? Can you, hold on.
4x cubed.
4x cubed. Yeah.
7x plus 8.
Plus 0x squared minus 7x?
Yeah.
Plus 8?
Yep.
Yeah, I can see right away that I'm not going to get 4x squared as an answer. Well, that tells me something. You can't use synthetic division maybe in this. Or at least you got to use it in a different way than I'm using it. In other words, if I use long division, here's how it plays out. You always divide that into that as your first step. That gives you 2x squared. Then you multiply the 2x squared by both terms. And then subtract, which gives you 2x squared. Bring down the remainder. Repeat. Divide 2x into 2x squared. You get just x. Multiply x by both terms. Subtract. Minus 7x minus a minus x gives you minus 6x. Bring down the 8 one last time. Subtract, you get a remainder of 5. So this becomes 5 divided by 2x minus 1. Oh, well, I learned something new every day. In other words, long division produced a different result than synthetically dividing by 1/2. I don't quite understand why. But we don't need to figure it out. In other words, you can always do long division on these. The key to this problem really is figuring out what to do with that remainder. Not everybody would realize that a remainder of 5 means that I'm adding 5 divided by 2x minus 1 to the answer. In other words, my answer is 2x squared plus x minus 3 plus 5 divided by 2x minus 1. All right. So she uses this box.
Yeah.
doesn't look like synthetic division. It doesn't look like long division. She
No, it has this
somehow
like
uses,
weird one.
yeah, it's a weird use of that box. It gives you the same answer as I get doing long division. I'm not sure it saves you anything. I don't think it's a quicker method.
Yeah, I think it's just easier
Yeah.
to understand.
Well, and doing question B, let's see if we get the same answer doing B using long division. In other words, what I'm going to have to do on B, I think, is do this. In other words, I got to add the dummy variable there and here. Like that. In other words, if I write it like that, now both my divisor and my dividend have all degrees of x. Let's see if I can get the right answer. 4x gives you 4x cubed plus 0, subtract minus 6x squared, bring down the 0x, repeat, minus 6 minus 6x squared plus 0x, hold back up. When I subtract, I get minus 6x squared plus 0x. I guess I have to bring down the 5 also. Now, when I multiply, that gives me minus 6x squared minus 0x plus 24. And now I've got a remainder of minus 19. So my answer should be, let's see if that's what she got. 4x minus 6 plus 16x minus 19 over x squared. Wow. So I guess I don't know how to do long division when you have dummy variables required. I didn't realize I didn't know how to do that. I didn't get the right answer. I got close, but my remainder is wrong. How would we get that remainder? 6x minus 19. I did something funky when I did that division. Let's see if I can figure out what it is. It can't be right to bring down both things at once. So let's just bring down the next term, divide it. That gives you minus 6. That's minus 6x squared minus 0x plus 24. Now when I subtract, I get minus 24. Bring down the remainder. Yeah, can't do it.
Negative
I'm
4.
not sure how to do it.
Negative 4 times 4x is negative 16x.
Oh, I never did that part, did I?
No, you forgot.
Oh, I left that out. I should be able to get the same answer she got here. So I'm multiplying 4x times all 3 terms. That was my mistake. I just multiplied it by 2 terms. Yeah, okay. Now when I subtract, I get 16x, bring down the 5, and that's the remainder. So it's plus 16x plus 5, all divided by x squared minus 4. So you can use long division. You just can't make arithmetic errors like I did. Yeah, there's nothing magical in her box method. I want to make sure I add that word. All right, so that's 19A and B. Imaginary numbers. These are pretty simple. Let me just go through this with you real quick. I is equal to the square root of -1. I squared is therefore equal to what?
1.
-1.
Or -1. Yeah.
I cubed is equal to I times -1, which is -I. And I to the fourth is -1 times -1, that's 1. Now everything repeats. In case you didn't know, I to the fifth is I to the sixth is I squared, or -1. I to the seventh is the same as I cubed, or -I. I to the eighth is the same as I to the fourth, which is the same as 1. So what's I to the 10th equal to?
-1.
Yeah. In other words, what you do is you divide that number by 4 and deal with just the remainder. In other words, that's the same as I to the squared. If I had I to the 503rd, what's that equal to?
-I.
Divide that by 4, and whatever your remainder is what the power is. I cubed, which is -I. In other words, first of all, any number that's 100 is divisible by 4. 100 is divisible by 4, 200 is divisible by 4, 700 is divisible by 4. So when we have a number like 503 and we divide it by 4, we know that's our remainder, 3. Okay? So I to the 71st here, just a second. Let me see if these are on the other one. I hate to be looking at the answers when I'm looking. No. So A through F are not. Now let me guess that my key went away also. Yeah, here's my key though. All right. Let me copy these and then I'll go through them one by one. So we got I to the 71st. We've got I to the 61st. We got I to the 90th. And we got I to the 104th. And then we got a couple of other problems. 5I divided by 2 plus I times root 5. And finally we have 4 minus 3I divided by 7 minus 10I. All right, let's get rid of the easy ones first. What's I to the 71st power? Same as?
-I. Well, I see.
Well, don't use negatives. Divide it by 4, and whatever your remainder is, that's what the answer is.
The remainder is I to the third.
What's I to the 61st?
The remainder of I.
I to the 90th.
A remainder of I squared.
Not the remainder, that's the equivalent. What's I to the 104th? I to the 0, right? In other words, if I divide this by 4, I get a 0 remainder. Now, I to the 0 is the same as I to the 4th. Anything to the 0th power is 1, which happens to be also I to the 4th. I squared is -1. I to the 1st is square root of -1. I to the 3rd is negative I squared, -1, or negative I, or negative square root of -1. So if they want numerical answers, these are the numerical answers. If they want, and they almost certainly want numerical answers. They don't want you to say I squared as an answer. Okay? So the only hard one there was really this one. When you get a 0 remainder, that means it's the same as I to the 4th. Notice that I to the 4th was the same as I to the 8th, which is the same as I to the 12th. They're all perfectly divisible by 4. So that's the easy ones. Now, let's take these one at a time. This is not really a division problem. Just looks like it. If I gave you this problem right here, that looks like a division problem, right? It's not. What it is I'm going to rationalize the denominator. It's really a multiplication problem to get that. So whenever you have an irrational denominator, you have to rationalize it. It's not really a division problem. It's a rationalization problem. Same thing is true with imaginary numbers. Whenever you have a division problem, the only thing you really have to do is make the denominator real. So you're not rationalizing it, you're realifying it. And the way you always make the denominator real is by multiplying it by its conjugate, which is 2 minus I root 5. In other words, the conjugate is always the same two terms, different sign. And since I multiply the bottom by that, I got to multiply the top by that. Now, what I'm going to get in the bottom is going to be 4 minus 5I squared. If you FOIL those two terms, that's what you get. And the beautiful thing is that I squared is a real number. What is I squared?
-1.
So the bottom becomes 9. Now, the top is still an imaginary number. It's 10I minus root 5I squared. Well, I squared is -1, so I can do that. And now, that's my answer. And while I still have an imaginary numerator, I have a real denominator. And that's the whole point of these problems, is to merely make the denominator real. This doesn't seem to have any relationship to that, but trust me, that is the correct answer. Okay, now let's have you do the second one, which also looks like a division problem, but it really isn't. It's a realifying problem. What do I do here? What do I multiply?
Multiply 7 plus 10i.
By both top and bottom. In other words, a very important concept is when you're dealing with fractions, the only thing you're allowed to do is multiply by the number 1. That's it. I can't multiply by the number 2 because I changed the fraction. But I can multiply any fraction by the number 1 without changing it. Well, here's my number 1. 7 plus 10i over 7 plus 10i. Okay? What's that give you in the bottom? It's always, notice what the bottom is. It's difference of perfect squares multiplied back together again. So what are you going to get? You're going to get 49.
Minus 100 IQ, or I squared, or I guess plus 7di minus 7di.
Which cancel. So the two middle terms always cancel.
And then minus 100 I squared.
Right. So what is my new denominator in real number terms?
149.
What's my new? Let's multiply the numerators. I'm going to FOIL the two numerators. I'll do it real quick. 28. Let's see, minus 21i plus 40i is plus 19i. And then minus 3i times 10i is minus 30i squared. Simplify the numerator.
58 plus 19i.
Good. And there's your answer. Now, there's one possible scenario where that would not be an acceptable answer. And that's if they said, give your answer in proper A plus BI format. This is really the proper format for a complex number, where A is a real number, B is a real number, but this is the real part of the complex number, this is the imaginary part. Okay? So if they wanted this answer in A plus BI format, I would have to separate it into two fractions. That fraction plus that fraction. So I'd end up with 58 divided by 149 plus 19 divided by 149i. That's in A plus BI format. Let's see if she gave it in that format. No, she left it in the standard. 58 plus 19i over 149. Because all that means is that she didn't require it in A plus BI format. Alright. I believe the rest of these are on my original sheets.
Yeah, we finished all until 21.
Nah, she still doesn't have a 21A or B in there. All right, let's find 21A and B. I'm sorry, I should have seen that. Let me write these. We'll solve them. So 21A is y equals 2x squared plus 5x minus 3. And also y equals x squared plus 4x plus 3. What method are we going to use to solve this?
Elimination.
Well, we could, I suppose, use elimination, but actually substitution works better. Notice that the y's are the same. We're looking at a system of equations. So this y equals that y, which means I can do what?
Make them equal to each other.
And then solve them. In other words, I'm really doing substitution with this method. Okay, now we're going to gather everything on one side. Factor that.
X plus 3 and x minus 2.
So your solutions are what?
Negative 3 and 2.
So there's two solutions for x. So we need to go back up into either of these equations, that's the shortest one, and plug in 2 for x and also plug in minus 3 for x. Let's start with the minus 3. In other words, what is y when x is minus 3? Well, it's 9 minus 12 plus 3, 0. So the y that goes with the minus 3 is 0, and the y that goes with the 2, y, you see what I'm doing over here on the left, is even this notation's a little strange, but you should follow it, I'm sure. So the y that goes with the x equal 2 is 15. So the solution looks like this. Minus 3 comma 0 and 2 comma 15. Those two right there are the two solutions to these system of equations. And you have to write it like that. You can't say x is minus 3 or 2 and y is 15 or 0. Because the 0 only goes with the minus 3 solution and the 15 only goes with the 2 solution. So you kind of have to write it like this. And b, let me write it real quick. How am I going to solve this?
I'm not really.
Well, let me give you a hint. Solve it by substitution. So what do you have to do first?
I'm not really good at these problems.
Okay. Let's take the second one. If I solve the second one for a, what do I get? A equals 100 divided by b squared. Now go into this and substitute what we just solved for a. So we got 70 equals, and instead of a, I'm going to write 100 over b squared times b to the 5th. So 70 equals 100 b cubed. B cubed equals 7/10. B equals the cube root of 7/10. And then a, in other words, now if you go back up into either equation and plug in what we came up with for b, well, a is equal to 100 divided by b squared. So a equals 100 divided by this thing squared. Well, b squared must be 7/10 to the 2/3 power. And you see how I got that? If I square b, it's squaring both sides. So b squared equals 7/10 to the 1/3 squared, which is 7/10 to the 2/3. So there's a number for A, and there was a number for B, cube root of 7/10. So the key to this problem was also to solve it by substitution. But before you could use substitution, you had to solve for A. I guess we could have solved for B, but B would have been a little more complicated, because if I use the second equation to solve for B, I get a plus or minus. And then it considerably confuses the issue. So it's better to solve for A, because I've got a little a in both equations. So solve one of them for A and substitute in the other one. All right. Now we can go away from the key.
No, because 22 is still not on the key also.
Oh, it is? Okay. So C is on the key. C is on the other page. Oh, we did C. We did C, because the only one that was on there was 3 equations and 3 variables.
Yeah.
I can't quite see what she's doing on her key. Oh, I see what she's doing. She multiplied that equation by 2. Okay, she did it the same way I did it. She produces an equation 4 and 5 and then uses equations 4 and 5 to solve for the 2 variables, and then she works her way back and solves for all 3 variables. So we did C, and you're saying 22A is not on the key also, or is not on the original. So let's do that one. Let me write it first, and then we'll solve it. Cube root of x minus 1 over 10, all plus 3. All right. Work me through finding the inverse of this. First step.
You switch x and y.
So now I got x equals the cube root of y minus 1 over 10 plus 3. What's the next step? I'm trying to solve for y now.
Subtract.
Okay, so now I got x minus 3 equals cube root of y minus 1 over 10. Next step?
Times both sides by 10.
So that's 10x minus 30. Next step?
Cube both sides.
So 10x minus 30 cubed equals y minus 1. Last step, add 1. So 10x minus 30 cubed plus 1 is what the inverse is. Now, it's possible she wants you to simplify that, because I know it can be simplified, because when I cube this term, I get a number as my last term. So I would want to take that final number and add 1 to it. The question is does she do that in her key? I'd be surprised if she does that. No, she doesn't. She gives the answer exactly the way I gave it. So she does not simplify it. And that's usually true when you've got big exponents of binomial terms. They don't really expect you to multiply that out and find out what 10x minus 30 cubed is. If it was to the 5th, you would know they wouldn't want you to do it. When it's cubed, I'm never sure. Y equals 4/3 They're not going to give you a tough one here. There are some tough inverse problems, let me tell you, where you'd never figure them out if you didn't know the technique. Okay, so first thing I'm going to do is switch variables. These really just become algebra problems. Okay, what next?
Subtract 6 from both sides.
Subtract 6, and while I'm at it, I'm going to multiply by the reciprocal of 4/3. So that's going to get rid of both that and that, right?
Mm-hmm.
In other words, I did 2 steps in one is all. Next step?
Cube root.
Okay, so this is equal to the cube root of 3/4 x minus 6, and then add 1 to the end of it, and you get y. And I suppose it's not really correct to call this y. It's not the same as this y. It's y inverse. That's really the way to write it. Is when you've switched variables and you solve for y, you're really solving for y inverse. You can't keep calling it y. It's not the same as this y here.
Okay.
Okay? So we really should switch variables and call that y inverse and solve for y inverse. Is really the way they should state it. Although I've never heard anybody state it that way. C is not tough. C is just more algebra. I don't think we need to cover it.
It's the last problem of this packet. We might as well do it since we have 10 minutes.
Okay, it's the last problem that we haven't done. We've done 23 and the ones below, haven't we?
Yep.
Okay, well let's do, this one is the last problem of the pack. So let's do what I said. We're going to switch variables, only I'm going to call this y inverse, not x. Just don't let it confuse you. I think the reason they don't teach it this way is that looks like 1 over y. In other words, if I said y to the minus 1, that is 1 over y. So notation can be a little bit tricky here. And that's why nobody does that. We'll call it y until we solve for it, and once we solve for it, we'll call it y inverse.
Okay.
Okay, what's the first step?
Subtract 20.
Next step?
Divide by 3.
Next step?
Multiply by 2.
Last step?
Add 9.
And put the inverse sign there. So that's y inverse. Now, since we got a few minutes, I'm surprised they didn't give you one, but I'm going to give you one. It's the inverse of that. How do you solve that for y? It's difficult, right?
Yeah.
Really difficult. In other words, I've got a quadratic here. If I can't factor it, and I can't solve it for y. But what if I use the quadratic formula? And this is the secret. Here's what I do. I bring the x to this side over here, treating it like it's a number, leaving 0 there. Okay? Now, I've got a quadratic. A is 1, B is -1, and c is 7 minus x. So I'm going to plug it into my quadratic formula. Y equals negative b plus or minus b squared minus 4 times 1 times c, which is 7 minus x, all over 2. That's my answer for y inverse. I mean, I can simplify it a little bit, but not a lot. So whenever you have an even power in x, it's always going to be hard to solve for y when you switch the variables. And the only way to do it is this rather sophisticated technique where you treat x like it's a number and you combine it with your number, and that becomes c. And that's a perfectly legitimate answer. It's just, it's only taught in, well, honors, maybe pre-calc classes. I halfway expected to run into it in your honors algebra class, but not terribly surprising that we didn't. But this is the way to do it. And it would be the same if it was x to the fourth. In other words, whenever you have odd powers, you can do it the normal way. But when you end up with a quadratic in y, you have to do it this unique, special way.
Okay.
All right. Nicholas, put in a lot of hard work. Feels to me like you've learned a little something.
Yeah, a lot.
Okay, good. I'm going to let you go, and hopefully that'll take care of you for a while.
Yeah, thank you.
You're welcome. Have a good week. I'll talk to you next time.
Okay, you too.